Good evening to all of you. I am Raghavan, Vice Chair of ISHRAE Technical Committee. I am very pleased to welcome all of you for this part 2 of the series on water titled Unraveling the Mysteries of Water in HVAC Systems. We had the part 1 session on 10th of this month. So this is our part 2 series. Through our different technical committees, ISHRAE brings the domain experts to share their knowledge and wisdom with the rest of the HVAC fraternity. So this series, which is presented by Mr. Charuchandra Dewasthale, is the chair of D102 Water Treatment Technical Committee from ISHRAE. He chairs the group. So representing that group, using his own personal wisdom, experience, he is going to share a lot of his thoughts on this part 2 of the 3-part series. In part 1, we had a look at a lot of interesting basic qualities of water like molecular structure, the conductivity, surface tension, diffusion, etc. So in part 2, we are going to move forward further. So he generated enough interest and curiosity of what are all we are going to learn in part 2 and part 3 of this series. We have got some very good reviews and feedback from many of the participants. So we are very happy to start the part 2 of this series, giving you more technical information, which we all could use in our professional field. Thank you. Before I hand over to Mr. Charu, a brief introduction about him in case some of you were not present for part 1 session. Mr. Charu is a mechanical engineer with more than 34 years experience. He initially worked for Thermax for their water and environment division. And for more than 25 years now, he is on his own offering professional services related to, again, sustainability, water conservation, etc. He is very passionate about sustainability. He already holds 2 patents on the water conservation related product, and 3 more patents are under assessment and review by the concerned body. He has already successfully saved 27 lakh liter of industrial oil from being discarded. So conservation also is one of his passionate subjects. So with all this background and experience, we are very happy to invite Mr. Charuchandra Dewasthale to present part 2 of this 3-part series. Thank you very much, and over to you, Mr. Charu.
Thanks a lot. Warm welcome to you all. My name is Charuchandra Dewasthale. I'm passionate about water and oil, the 2 natural resources which are very, very, very important to human race, or to everybody, not only human. So last time what we did was on interesting aspects and interesting things about water. I'll just recap them. But before that, I should tell you that I chair technical group of ISHRAE on water. It is titled as D102. And one sec, it is not. So what are the objectives of TG Water D102 is to make our ISHRAE members wise in water. Most of us who are handling water into our condensers or HVAC circuits, we say that water mein jhanjat hai yaar. So I want to remove that jhanjat from water and make it interesting. Remove the fear factor about water. When they say that I'm going to get tanker loads of water, they feel something will happen, bad will happen. So nothing bad will happen. It's okay. Water is water. Educate them on every aspect of water. So that's what we are going to do now. Publish a book on water. There is no book on water right now, which can be referred by even non-engineers into engineering language. So that's what we are aiming at, to take up and find solution to industry specific issues. Like the last month, one of my customer called and he said that he is not going to get he has to recycle the water of their ETP, and he is not going to get fresh water to that extent. So what can be done is using his ETP water into cooling water. But his problem was that TDS was almost around 15,000. So what to do? So this is an industry specific issue which needs to be resolved. Trouble-free use of water in condenser evaporator circuits, adiabatic operations, because they are all based on water and they need to be taken care of. Corrosion scale-free condensers evaporators, compilation of various technologies we will be doing. Study of water parameters and their impact on the water system performance. Treatment of water. Right now, there is a lot of treatment which is going on, and some treatments are really not required. So we will be talking about those. This is TG water agenda. Water saving is one area, and water recycling techniques from ETP or STP wherever we can. So related to water, everything we are going to touch base upon. So for that, here is one appeal which I want to make to everybody here, that we are a group of 9 people from HQ and some people are from HQ. We would like to increase the strength of our group, of our technical water group. So if you are interested, join us. We require good people. And you can WhatsApp your details on the following numbers. These 2 numbers are mine. First 2 numbers are mine. This number is of Arti's. You can connect to anyone. We will induct you into our group, and so that we will do this good job for ISHRAE and our society as such. So much. So shall I will start with the recapping whatever we did last time. Is water or magic? In our earlier session, we have seen importance of water, physical, chemical, thermal properties of water, and how entire world is benefited because of that. To give you one example, that water forms ice. Ice is more less dense in density of ice is less than water, so it floats. So how entire world is benefited? The creatures who are there into the sea, or they are into the lakes, they are protected. The upper crust is ice, which is a bad conductor of it. So the atmospheric negative temperature is not transmitted to the water, and water remains as water because of that ice which is floating. So every property of water which we discussed that time has a some meaning, and which are beneficial to us in the long run. Then we discussed about parameters of water, impact of each parameter, and common problems such as corrosion and scaling, which are normally faced by each and everybody in the world, I will say. From this today's session, the expected outcome can be better understanding of corrosion and scale phenomena. Then monitoring of parameters in your utility circuits. People are, when analysis of the water is to be done, they analyze everything in the water, which is not required. So monitoring of parameters, we will discuss what are the most required parameters of the water. Then the importance of proper material of construction at the design stage itself. For example, cupronickel tubes are used whenever there is a proximity to sea, and you are using sea water as a cooling water on once through basis. So that is a selection of proper materials at the construction stage, design stage itself, and simple tips to control corrosion and scaling. In our next session, we will be talking about water into HVAC circuits. Means we will be talking about cooling water. We will be talking about evaporator, means chilled water. Then we will be talking about water used into adiabatic operations. Then we will be talking about how to recycle that water and mitigation of problems such as corrosion and scaling. Today we will learn about corrosion and scaling phenomena. Next time is mitigation of that. So this was a 3-part series. Today is the second part. So I will just recap physical properties because these are required in today's session also. So let me repeat it this time again. See, water is colorless, odorless, tasteless. That all everybody knows. And it is a universal solvent from the perspective that it can dissolve anything which is connected with. So let it be gases, let it be solids, let it be liquids, whatever. Water boils at 100 degrees, freezes at 0, density is 1 gram per milliliter. See here, at 4 degrees. At 4 degrees. We take it as 1 in our normal day-to-day operations, but it is at 4 degrees. And water is a polar molecule. Taste of water. The taste of water is because of the solids and gases which get dissolved will give a typical smell or taste to the water. Hence, GI is given to the particular region. And give you one example of Aurangabad region. Means now it is called as Sambhajinagar. The beer tastes different when it is brewed in Sambhajinagar. So Sambhajinagar area is water starved area, but still most of the beer factories in Maharashtra are located in Sambhajinagar because the water quality is good. Then I came across mangoes. Mangoes, they have taste depending on which is the area it is grown. Like Devgarh mangoes taste differently in Devgarh, and that tastes differently in Kolhapur because the soil structure is different. So whenever water, whenever it is raining, the water comes into contact with the gases. So CO2 it comes into contact. CO2 gets dissolved into water, forms H2CO3. It touches into soil, and if at all any calcium is present, it forms calcium hydroxide, calcium oxide, calcium carbonates, calcium hydroxides, and then that gives one of the taste to the water is because of calcium. So the parameters of water which are very important are basically pH, TDS, total dissolved solids, then total hardness. Then there are two hardnesses which are there: total hardness calcium, total hardness magnesium. Then TSS is total suspended solids. Turbidity, I will be talking more about it. TBC, total viable count or total bacterial count, TBC or TBC. These two are the names it is known as. And chlorides. I have taken, you won't be surprised that I have taken chlorides. Why differently? That reason also will be known, we will be discussing. Now, these parameters are the main parameters of the water. They have impact on our systems. So each parameter we will go deeper, try to analyze those issues and problems associated with that parameter, and come out with the problem statement that what can go wrong. Now here I would like to tell you about, you can ask me question anytime during our session. The reason is sometimes you people are all working people. You must have received some kind of peculiar examples you can cite, and we can discuss the things right at that spot itself. So you just post the question in the chat box. I will look into, and I will take a small break. We will discuss, and then I go to the next topic. So what is pH? You must have, all of you have heard about pH, right? There is hardly anybody who doesn't know about pH. So what is that? Is very important parameters of water. It is basically negative logarithm of hydrogen ions concentration, but it plays a very, very important role in water chemistry. Very important role. Means how the water will behave into the system is decided by the small factor of pH. So let us know more about pH now. pH range is 0 to 14, out of which 0 is highly acidic and 14 is highly alkaline, and 7 is neutral. This can be tested with pH paper. There are pH indicator solutions available in the market. Then there are pH meters available in the market. So anyway, you can, these are all reliable kind of equipments or reliable kind of test which can be easily done. See this acidic range. Okay, 0 to 7 is this acidic range. Now, you start from 7, you go towards 0, the acidic intensity goes up, the activity goes up. Means 0 pH, which is normally not there, the slight number will be there, that will be highly acidic than 7. And when you go from 7 to 14, 14 is highly alkaline than 7. So alkalinity goes up from 0 to 7, 0 to 4, 7 to 14, and acidity goes up from 7 to 0. So acidity is directly connected with the corrosion, and alkalinity is directly connected with the deposition, fouling, etc. That we will look into at a greater, I will say, intensity. There will be more slides into. Now the pH is directly connected to corrosion, embrittlement. It has a polishing effect. It has a very slippery layer kind of it forms onto the metal surface. So all that thing will be there. I will give you one of that slippery layer. I will give you one small example. आपने कभी निरमा से हाथ धोए हैं क्या? कई बार we industrial people can, and we have used nirma. Now, when you wash your hands with nirma, what happens is nirma contains good amount of caustic, and good amount of water also cannot remove that caustic. It is still slippery. It is still, you can feel something on your hand. So that is pH which is higher in the in nirma. Now pH value goes below 5, both iron and copper will rust rapidly. The rusting will take place, means corrosion will take place when the pH is below 5. And when the pH values are higher than 7, both iron and copper are usually protected. So now summing these two together, 5 to 9, pH between 5 to 9, pitting will likely to occur if at all the protective film is not formed. So one of the thing which is there done by the chemistry is to form a protective film over the surface. If pH is more than 10, then what will happen? Dangerous. Corrosion can take place, embrittlement can take place. If at all it is in connection with the contact with the copper or aluminium, the corrosion will be terrific in this thing in nature. So the pH should be, means of all our systems, we have designed the treatment is between 6 means slightly acidic, but normally 7 to 9. That's the pH range we operate into our usual systems. In the acidic solution, means when the pH is below 4, the corrosion rate increases due to availability of H ions, which undergo cathodic reaction of hydrogen evolution, and which is as follows, means H2 will be formed. In the intermediate pH range, means from pH 4 to 10, the corrosion rate remains nearly constant due to formation of porous ferrous oxide on the metal surface. In this case, the corrosion rate is controlled by oxygen transfer through this porous deposit layer to the metal surface. The cathodic reaction means it forms a hydroxide. I'll tell you what is the meaning of these two. See, whenever you go from 7 to 0, the corrosion rates goes up substantially, and that is because availability of H plus which is there, and cathodic reaction takes place and hydrogen gets evolved. Okay. Now, whenever you are going from say pH 7 to 10 or 10 and above, then the ferrous oxide deposits will get formed and oxygen will attack through that. In this case, people go in for formation of ferric oxide, which is black in color, and that will take care of this kind of, I will say, corrosion reactions. So again, I'm repeating that 7 to 9 is the safest range if at all some film forming agent is applied to the surface. At pH value above 10, the corrosion rate goes exponentially high and should be avoided. Rate of fouling will also go substantially. Rate of fouling means what will happen is it will create a congenial atmosphere for algae to grow. algae is film forming in nature. So algae will travel along into the pipeline and gets deposited there. And this is can deposit onto our condenser tubes also. And that is how the fouling will start. But the trigger to the fouling is from pH, which is higher than 10. From the practical point of view, corrosion problems occur at lower pH of the system, means 7 and below, while scale and fouling problems arise at higher pH values, means 7 and 14. These are the ranges of uh, uh, pHs which is connected with the fouling or corrosion or scaling issues. This is another more important factor is total hardness. Total hardness is hardness caused by dissolved solids, which are primarily cations like calcium, magnesium, ferrous, ferric, zinc. You name any cation which is there into water. But to us, the significance is calcium and magnesium. That's why in our earlier slides you are saying total hardness calcium, total hardness magnesium. These two are the ions which are directly connected to the scaling into the water. So they are only considered. Rest of the things are not, ions are not considered because they are also available in very, very small quantities. I mean, it is so insignificant that it will not have any impact on the water parameters or water behavioral issues. Total hardness is the sum of calcium and magnesium ion concentrates expressed as calcium carbonate in milligram per liter basis. That is what we call it as ppm. So how much is the ppm of your hardness of your water? 57. 57 means 57 milligrams of calcium carbonate and magnesium carbonate are present per liter of water. Okay. So total hardness is mainly responsible for scaling. Now total solids. Aarti ma'am, how do I look at somebody has posted any question? I'm not able to see.
You can click the question and answer symbol
No,
at the
I
bottom.
cannot see
As
the
of now, there is none.
Yeah, but there is no chat box here. That's why I could not see the chat here. That bar which is there, which shows speaker.
No issues. Whenever you are ready, prompt me. I will
Okay.
read it out for you.
Okay. So total solids are total suspended solids and total dissolved solids. Now, total suspended solids is TSS and total dissolved solids is TDS. Okay. Now, this decides the rate of corrosion, scaling, and deposition. Very important parameter in the operation. Each of these parameters like TSS and TDS, we will look at it very deeply into the next slides. But I'll give you the how much it is. There is a IS standard IS 10392 in case of boiler operations, where it talks about TDS should not go above 3000 level, or cooling water, which is generally between 2500 to 3000 level, that TDS should not go. If water is with higher TDS, then blowdowns are to be higher. And if at all we want to reduce blowdowns in order to save the water, then TDS value will go up. Again, it is not congenial for our operations. So to reduce the blowdowns, you can reduce the blowdowns. That's basically the area. Sir, yeah, they're recording until later stage. Okay. So in case you want to have a higher TDS, then blowdown are to be higher. In that case, you reduce the blowdowns and reduce the TDS thereafter. So I will elaborate it further. Total suspended solids is TSS. TSS value is more important into utility circuits like cooling water, where it is coming from external source. Give you one example here. That area of Vapi, very densely populated area, industrially very densely populated area. And most of the units there, means heaters and boilers, are burning solid fuel, including coal, and that entire thing goes into the up in the sky. Now, when the cooling water sucks fresh air from the terrace, what it sucks is all this uh, dirt, dust, unburnt carbon gases, everything. It sucks and puts it into the cooling water. Now the two problems arise. The TSS value of WAPI cooling waters are very high. This is one. And second is pH is always suppressed. Being they are putting more acidity into the cooling water due to CO2 which is getting dissolved, and they have a problem of corrosion into the system. This TSS is responsible for depositions in the circuit and are treated as a part of scaling itself. But still, two things are different. Means that's why I am giving emphasis here that TDS is the source which is a major source for scaling. TSS is the source or major source for depositions. These two are the different phenomena. They are not interchangeable also, and they are interrelated in a way, because whenever there is a scaling, deposition will take place, or whenever there is a deposition, scaling tendency will increase. Both ways it goes. Now, there is a major difference in these two. Is scaling is very hard and very difficult to remove, whereas deposition is very soft and comparatively very easier to be removed. These two are the examples here. Now, there is one more factor which is there into cooling water chemistry, that is turbidity. I will give you one example here, that whichever cola you like, it can be Coca-Cola or Pepsi or Thumbs Up or whichever, that Coca-Cola water or the Thumbs Up water is turbid in nature. Though it is very clear, there is no suspended solids. You can see through those through the I will say through the glass, but that is called as turbid water. Means this is a definition of turbidity, that suspended matter such as clay, silt, finely divided inorganic, organic components, color are all form a turbidity. These are very minute in nature. They impart color to the water because they are always in suspension. It is very difficult for that size to get settled into somewhere. So it is always remaining in suspension. This turbidity will play havoc when it is in cooling water area. So in case of cooling water, excess turbidity can form deposits on the heat transfer area. Plus, it induces microbial contamination and issues in the cooling water circuit. So turbidity needs to be controlled completely and absolutely. TSS and turbidity, they are interrelated from the perspective that turbidity also is a component of total suspended solids. But the particle size of in case of turbidity is very small, so uncyclable, unfilterable, that kind of. Water is a conductive medium. Yes, you can easily conduct electricity. You can easily conduct heat through water, and ability of the solution to conduct electrical current directly proportional to the ions present and their concentration. Means the TDS value goes up, the conductivity goes up. Total dissolved substances go up, the conductivity will go up. So solutions of mostly inorganic salts, acids, alkali show a very good conductivity, whereas I remove everything from water and make it H2O only, then it will not be conductive. Pure H2O is not very conductive. Molecules of organic compounds that don't dissociate will not show any conductivity. They will be very poor conductivity in the circuit. So conductivity is directly connected with the total dissolved solids. So there is a connection we have established, that conductivity and TDS as interconnected. So what we do is we take the case of conductivity reading and multiply it by this fixed number. This fixed number is the thing. 0.55 to 0.90. This number we multiply, and this is how the conductivity can be calculated. Fresh distilled water conductivity will be 0.5 to 2 micros MHOs per cm, whereas potable water will be very conductive water. But ultimately, conductivity is directly connected to TDS, so it is directly connected to scaling. What is total alkalinity? TA, total alkalinity. It is the capacity of water to neutralize acids. Means what it contains? It contains all anionic components, sulfates, chlorides, all those hydroxides, oxides. These are all very. Am I audible? My internet connection seems to be unstable right now. So, these are all, means anionic component is called as alkalinity. So it is expressed as P alkalinity, M alkalinity, phenolphthalein alkalinity, methyl orange alkalinity, and directly connected with the corrosion and deposition portion, but that we have already seen that it happens like that. So total alkalinity is another area we should look out. Chloride. Chloride indicates only chloride anions present. Means how many are the chlorides and anions are present in the circuit? There. Why they are important? One, they contribute to corrosion. This is one. Second is chloride ions are not affected by any of the treatment philosophies. Means chloride will remain same. So whenever we are designing any kind of blow down rates, the entire blow down rate is decided by devised on chloride ions. Means how many times chloride ions have been going into. Give you one example. Suppose your inlet water has a chloride of 20 and your outlet water is 300. So you are giving blow down there. So you calculated in the blow down that it is 300. How many times this 20 got multiplied is 15 to make it 300. That means the blow down is about 5 to 7%. So in case I have to decrease that blow down, then I make it 20, means 20 times the multiplication. So 20 into 20 is 400. Okay. So that flow 400 becomes that criteria, means I will say value of chloride into that cooling water. Now, why chloride? Because chloride is generally not affected by any of this treatment methodology, except demineralization. Means demineralization will remove chlorides completely and absolutely from the system. And how much it will go to? It will make it zero when the entire water is demineralized. Means demineralized is no cations, no anions, pure H2 is present. That is demineralization. Sulfates. Sulfates normally occur in the water, and whenever we are devising any system treatment philosophy, we use sulfuric acid and convert carbonates, means CO3 ions, means calcium carbonate, CaCO3. Okay, that we convert into calcium sulfate, means CaSO4, through the use of this sulfuric acid. Now, why we do that? Because calcium sulfate has a tendency to come out in the and appear as scales, whereas calcium sulfate has infinite dissolving capability. Means it has very less tendency to come onto the surface and form the scales. That's one of the case with the sulfates. But sulfates are they are more soluble in than the carbonates, and basically they don't appear as scales into the circuit, but they can form very insoluble hard scales when they come into contact with any other cations like barium, calcium, strontium, etc. So, what are the sulfates? Sulfates have a scaling tendency, and there is a microbial contamination which is occurring, like sulfate reducing bacteria. This is normal in case of our chilled water and cooling water areas, more into chilled water side. These sulfate reducing bacteria have a tendency to form a film over the surface. They form colony over the surface, and they have a tendency to secrete acid below the ground. So if at all you have a pinhole into your chill water system, that might be one of the cases SRBs. Then there is NBs also, which create problem. So SRBs is another area which can create problem. So sulfate reducing bacteria are need to be taken care of. So they are going to be there. We how to take care of, we will look into. I mean, I have introduced more sulfates into further slides. Phosphates is very, very important to control corrosion and scaling. Very important. Phosphorus appears in water as phosphates. They can be classified as ortho, para, contains, organically bound, phosphonates. They are organic in nature. So there is lot of phosphate available in the water and mainly used as a scale cum corrosion inhibitor. Whenever there is a phosphate in the water, systems are protected from the point of view of corrosion. At the same time, in case of agriculture, phosphate is used as a fertilizer. So whenever you use phosphate into the water, you are allowing or encouraging your algae to grow faster and more, creating a problem to you only. So phosphates also can boost your green algae into your water. So that is another negative aspect of phosphate, which should be taken care of. Then there is whenever we go for swimming, there is the water smells chlorine there. Okay. Because water contains some free residual chlorine into this water. There is a saying in the market that chlorine को जरा थोड़ा free residual chlorine जरा ज़्यादा रखना. Normally, how much it is kept? It is kept at 0.2, 0.5, that basis, ppm basis. So barely there is some chlorine, but still there is some chlorine inside. Sufficient chlorine is there into the. This is chlorine is applied in the water at elemental form, means as nacet chlorine, or hypochlorite form, means NaOCl form, OCl form. In both the cases, it can be calculated how much chlorine is dosed, so that your free residual chlorine (FRC) should not cross this 0.2 to 0.5. Now, in case of water means because of contaminants like organic and inorganic, I will say contaminants. Plus, there is ample sunlight. India is a very warm country, so warmth, ample sunshine. So all are elements of growth for any bioorganism. So algae, bacteria, fungi, slime, all they are thrive into this. And because of excessive microorganism, variety of problems can be created. First problem is fouling, then flow restrictions, plugging of the tubes, under deposit corrosion, wood decay. They are all directly connected with the algae and bacteria. But this is diagram which is connected with the cooling water, and cooling water is more connected with these bacteria. Corrosion, biofouling, deposit, and scaling. These are the 4 issues cooling water faces. Out of which, if I solve the problem of corrosion, I will say I will consider the problem doesn't get solved because they are interconnected in nature. So again, corrosion will reappear even if you have solved it. So in case of cooling water, you have to take entire view as holistic view of this solving those 4 issues. You cannot just solve one issue. So similarly, this kind of microorganisms, you have to take care of algae, bacteria, fungi, slime, everything put together. So there are good biocides like chlorine. They are openly, they create good, I will say, treatment philosophy for algae, bacteria, fungi. So they use as broad-based algaecide, fungicide, etc. In case of cooling water, the treatment of water is, these are the one of the major areas to be looked into. Now, this dilemma you must be facing. So I thought I'll just add it into. See, ये तराजू है. Okay. On one side of the pan, it is scaling and other is corrosion. So if I want to reduce the corrosion, the scaling tendency will go up. If I'm reducing the scaling, then corrosive tendency will go up. So whenever I'm designing the process or designing the treatment, I have to balance it together. So scaling will not take place. At the same time, corrosion will be under control. So my system will give me better life services and better longer life services in the coming years. Now there are some gases in water. So oxygen also gets dissolved into water, as well as CO2 also gets dissolved. Now I'll give you one specific example here, that there is a tap water and I take 3 samples of tap water, the same water, tap water. One is at the room temperature, means that is a tap. I open that tap and keep it into one glass. Second, I take it like I put it into hot kettle, boil it and keep it in front of you. And the third glass is comfortably cooled refrigeration, means fridge. उसमें से पानी निकाल के I am giving you water to drink. Now, the taste of these 3 waters will be same or different. You can put it into chat box. Sajid Shankar ji, there is some IS standard for condenser circulating water. I will get you the number. Send me your email ID and phone numbers if possible. I can WhatsApp you or I can email you about IS standards of cooling water. Chilled water, I have my doubt whether there is a IS standard. But in case of cooling water, there is definitely IS standard available for cooling water. Cooling water, yeah. Now, the taste of this water will be same or different. The water taste will be different. Why? Because at room temperature, there is a 8 ppm of oxygen has gone into water. When you boil water, the oxygen gets out. So the taste of water will change. And when you chill the water, there is a good amount of oxygen can get dissolved. So in case of chilled water, the ppm of oxygen into chilled water can be as high as 12 versus 8 into room temperature and versus very less into hot water. So many of you must be handling boilers where you must be seeing that when you take out the water, which is condensate water, there are 2 advantages. One is you save water and you save energy because you are giving hot water to the boiler feed. Plus, whenever it is the water which is hot, the less amount of oxygen remains into the water, and that's how the taste of the water will be different. Shanku Vardhan sir is saying room water tastes good. Sir, any water tastes good, sir. Ultimately, Manar Patil ji is saying that it is different taste. And Sajid sir has given his number. So I will post you that. I will post you the details on your WhatsApp number. So basically, taste of the water is directly connected with the dissolved gases. That's what I mean to say. So what happens with oxygen going into? It stimulates corrosive reaction. So corrosion is very high in case of water. Why? Because oxygen hai, so oxygen will always be corrosive. So that's basically the case. It stimulates the corrosion reaction. CO2 is considered in relation with the calcium hardness. Means higher the amount of CO2, the more is the calcium hardness. And calcium hardness, basically, ये जो देन है, who gives you calcium hardness is carbon dioxide. So higher amount of carbon dioxide up to the air, the calcium hardness will be going up. Same is the case with some gases which are coming out with the pollution or process leakages. I will give you one example here that some gas that area was very marshy land. It was, and it was filled up with soil, and some office structures have been erected there. The whatever that marshy land has, it gives some kind of gases out, and people say that it is H2S and ammonia and that kind of. It is so much polluting that the compressor means these laptops, your big computer systems, they fail because of that corrosion, which is because of those gases. So gases emanate from the pollution and process leakages are dangerous. Ammonia is present into various forms in wastewater. Ammonia and copper relationships, they are absolutely not in tune with each other. So ammonia corrodes the copper systems very fast. Hydrogen sulfide and sulfur dioxide will accelerate the corrosion of the most of the metals. Now you will understand that the split air conditioners, the condensers are normally kept outside. In our IDC, means Maharashtra Industrial Development Corporation, we have a chemical parts, we have mechanical parts, etc. So in case of chemical parts, the split air conditioners, the condensers kept out of office or outside in the fresh air, they corrode very fast. Means I have seen that people are changing their condenser every after 6 months. So it is a corrosion, and that is because of SO2. Now we talk about CO2, oxygen. Oxygen dissolves into water, probably the most troublesome corrosive producing substance. The product of corrosion of iron by oxygen is containing iron oxides, is called as rust. So rust is coming out, means two electrons are getting free, hydroxide is getting formed, and ferrous or hydroxide takes care of the issues which are there into, as referred to us as corrosion. Now, what is the process of oxygen? Is it depolarizes cathode, means it defunctions cathode, so oxidizes ferrous to ferric, which forms insoluble ferric hydroxide. In the closed loop circuits, this will go on continuing till the time CO2 is present. But when they are open loop, like you have a hot and cold kind of circuit, so oxygen ingress is there, and then the reaction of corrosion continues. So oxygen needs to be taken care of into the system. So what we do in case of boiler, we add chemicals which can literally eat oxygen into the water from the water. But in case of cooling water or chilled water, what we do is we create a kind of film which will not allow the oxygen molecule to attack to the bare metal. How? And this is elaborated in the next session. So I will not invest my time right now. But the corrosion reactions these are the philosophies. Why? Because cooling water or chilled water is not aggressive in nature, but versus boiler is very aggressive in nature. So these are the things which are normally taken into account, and the treatment philosophy is devised. CO2 is comparatively less aggressive, and but it is corrosive. But the corrosion it is imparting more of a scaling tendency rather than corrosive tendency. CO2 dissolved in water is not as corrosive as oxygen dissolved in water. I will give you one super example here, that if whatever cola you like, means I asked you last time or in few slides ago, that which cola do you like? So it can be Pepsi or Coca-Cola or Thumbs Up. These are the three available colas right now. And if I give you Thumbs Up water without any soda in it, would you like it? I don't think you would like it. Why? Because it is flat. We say it is flat. जो हम लोग सोडा लेते हैं, when we put it into our drinks, and then we say that the soda is flat, it is like water. Okay, that tanginess is not there because of CO2. Okay, now that CO2 gets dissolved into water, like they have that whatever formula thumbs up has. So that water is created containing thumbs up, and CO2 is injected from outside. And that injection of CO2 is taking place at 3 degree. So at 3 degree, highest amount of CO2 goes into water at minimum possible time. That is why that 3 degree is very important. So whenever they get the chance, they descale that heat exchanger. It's a plate type heat exchanger, and one side is brine, and the other side is or one side is chilled water and other side chilled water containing some amount of glycol, and other side is Coca-Cola water or thumbs up water, and the at 3 degree CO2 is injected inside. So I will sum it up. Hardness, scale deposit formation, alkalinity, foaming, corrosion, scaling. These are the issues. Iron, corrosion and deposits, sodium corrosion, chlorides corrosion, sulfates corrosion, fouling, scaling again. Silica, uh, in our case, I have not discussed silica at length because our water is not so aggressive. Aggressive water is boiler, where silica plays havoc. And if it is a power plant boiler, silica will play very, very high havocs. But then in case of us, being temperatures are low, silica doesn't play too much to us. So I have not touched it. Oxygen corrosion, CO2 corrosion, hydrogen sulfide corrosion, fouling, ammonia corrosion, oil and grease, very high amount of corrosion and fouling, very high amount. Means small oil and grease into water can create havoc. I remember I was giving one training program to Philippine company, and I was talking about all these water related issues I was addressing to. The owner said, you should talk more about oil and grease, because in our case oil and grease is comparatively very low into the water. In his case, oil and grease was so high that he said that my entire cooling tower has collapsed twice because of fouling and generation of algae. Suspended solids, basically deposits. Organics, basically fouling. Dissolved solids, corrosion, foaming, scaling issues. Dissolved gases, again corrosion. And biological matter, corrosion and fouling. So these are whatever we have done till now. I have sum it up into these small slides which are there. Now, scale formation problems in water systems. We are now looking at how the scale gets formed. The scales have formation is causing significant problems in thermal systems such as desalination plants, steam generators in power plant. Nearly 20 to 30% area is provided to address the scale and the scale formation issue. High pressures are required to overcome the resistance caused by scale deposits, because they form that scale, and the flow restrictions will cause an uneven scale deposition can lead to pitting corrosion. Very high pH levels on prolonged exposure can cause caustic embrittlement. Now, these scales are comparatively low in our case because our temperatures are low. Now, I will give you one typical how the scale formation takes place. Which are the cations which are present. These are basically calcium and magnesium we talked about. So calcium carbonates, sulfates, and magnesium hydroxides. These are the major issues which are major salts which are there. The suspended particles like silica, which also plays a very major role, and corrosion products like iron oxide and copper salts. So these all get together, get heated, form the kind of eutectic bonds, and the scale is formed with the metal layer. So what is the mechanism of scale formation? scale formation constituents are present in the water as ions. So major cations, calcium, magnesium, anions, carbonates, bicarbonates, sulfates, chlorides. Major. Certain combination of these ions form components which are low solubility in water, or they have a reverse solubility in water. I'll give you one example here. Take the case of uh, sodium chloride. Sodium chloride means our common salt. This common salt, you dissolve into water, it goes in. Then you put furthermore, it goes in. Put still furthermore, it goes in. So there is, at one point of time, the solution will become saturated, means it will not allow any sodium chloride to be taken inside. So what it will be there? It will be settled on the bottom of the vessel. Now you heat it. What it goes? It goes into the water. So whenever you temperature, the salt concentration can be increased, or dissolving capability of any salt goes up. Okay. Now, Mr. Manoj Manikanda has asked how to calculate bleed-off rates based on water quality analysis for cooling water and evaporative cooling sum. Sir, this topic I will take into our chloride section. It will be easier for me to talk upon. And I have taken very special slides on this in our next session, on third session, which is directly related to water, our water, means HVAC water. So I'll touch upon this question into the cooling chloride section. And there is one more question, which is, yeah, IS standard. This is there. Now, what happens when the concentration exceeds? We already spoke about concentration of TDS. So in case of boiler, IS 10392 says that it should be 3000, not exceeding 3000. So what we give that time is blowdown. The water is taken out and the fresh water comes inside, which has a very low TDS value. So combining these two, we can have okay kind of range into the TDS range. But now here what is happening when you are giving blowdown of the hot water, that means you are draining away energy. Okay. So, and water also, because water is also precious. And the new fresh water is coming in, which is at room temperature. So it is going to cool your basic water, which is there into boiler. Same is the case with cooling water also. Whenever cooling water you have the TDS which is getting concentrated over the period of time, and that concentrated salts are taken off the cooling water basin through a blowdown, and the new fresh water comes inside. This new fresh water coming inside is called as makeup water. The water which is going away from the cooling water in the form of blowdown is called as blowdown water. This new water has a very less TDS value. So combining these two, I will say, figures, the reasonable figure emerges, which is of TDS, which is very much less to our the governing scale. So I take it other way around now. The salt concentration increases, the precipitation tendency will increase. That is called as reverse solubility. Calcium carbonate goes into water, it gets dissolved, but at the same time it comes back as scale, because this reverse solubility comes into picture. It emerges again as solids. Those solids are very sticky in nature and they have a very high affinity towards metal. So they stick to the metals, get hard baked and form scales. So both ways it goes. So I will just read it out. Once the concentration exceeds, the compound precipitates as solid. The precipitated solids may either remain in suspension in water as sludge, or they will form coherent scale bond with the metal surface, and that is the beginning of scale formation. I go next. So major factors affecting the scale formation are salt type and concentration. So now you will understand that whenever you say that I give soft water, that is you are converting your calcium salts to sodium salts. So you are increasing the dissolving tendency of any salt. Sodium chloride, even if it forms a scale, you can easily remove by nails. Na? It is so soft in nature because it is sodium salt. When it is calcium salt, it is so hard that you have to take some pointed kind of object to remove it. So that's the difference between scale type and concentration. The time period for scale formation. There are some areas where scale formation is very quick and fast. Very quick and fast. Take the case of Hyderabad region, where scaling tendencies are itself are so high that they form very fast scales very fast. Then hydrodynamics and fluid velocity. So in case of if at all you keep a very turbulent flow, then the tendency of scaling comparatively comes down. Or if the flow velocity is higher, the turbulence is created, the scale forming tendency is higher. That is why in case of coil type boilers, the coil is always remaining clean from the perspective of, because velocity is the highest that time. Okay. Now, same analogy when you use it into heat exchangers, the velocity suddenly is dropped suddenly, and through say 3-inch pipe, suddenly it is going into the area which is about 1 meter diameter. So the velocity has reduced. So the flow has is been divided, and the tendency to settle down at these low flow rates will be higher in case of condenser. So condenser will get choked. Operating parameters, operating temperatures, higher the temperature, low, more is the scaling tendency. And pH of water, we have already seen how pH of water, if at all pH is low, it is corrosive in nature. If it is very high, then it is scale forming in nature. So both ways it affects. Fouling deposits increase directly with the concentration of calcium sulfate. Now, why I have taken calcium sulfate as a salt here is because calcium sulfate, if at all calcium carbonate are higher in case of any water, then we add some small amount of H2SO4, means sulfuric acid, into water and turn those calcium carbonate to calcium sulfate, because calcium sulfate has a better solubility and better remaining in kind of water, means they will not form scales so much. So we do that. But what happens if at all हमारा ज़्यादा acid आ गया circuit में, then what it will have? Very high amount of corrosion, very high amount of corrosion. So this is to be very taken care of. There are calculation methods, and then only the acid is to be added. But once we add this calcium, means calcium sulfate is higher, then the deposit fouling will go up. Deposit tendency will go up. Microbial contaminations will go up, and circulating fluid will create another set of issues to the water. But comparatively, it will not have the scaling tendencies as of earlier water. This direct effect of salt concentration on the fouling is known as thermodynamic driving force for scale formation. It is supersaturation of the salt. Basically, salts get supersaturated and then it has a tendency to film form or appear as salt. So increasing salt concentration in water will increase the super concentration of the salts, leading to more depositions. That's what we say ना कि मुझे पानी बचाना है तो मुझे blow down कम करना है. If at all I reduce the blow down, my water parameters will go up. My water parameters will go up. The scaling tendency will go up. So they are to be balanced. That's the only thing I wanted to talk about. All these things are to be balanced perfectly. This is where the people come into picture. Scales is always present at higher pH value. The scaling tendency are more when the pH value are above 9, actually, or not above 7. Means here I just want to show that pH is alkaline in nature, whereas corrosion increases sharply with the decrease in pH. Okay, this we have seen. Precise control of pH is between 6 to 9. Avoid both scale and corrosion issues in the in the system. In practice, acid is dosed in many plants to reduce the scale formation, but this acid has to be very calculative and very, you should not, you should do it with the experts whenever they are there. This generates corrosion problems. In either corrosion inhibitor is to be added or precise control of pH around 6 to 7 is to be maintained so that there is no acidity developed into the system. So interaction between corrosion and scale in water systems can be mitigated by specially formed thin layer so that the scales also and the corrosion protection also can be given. Now, how we develop this thin layer also is of molecules, na? So the distance between these molecules should be less than thickness or size of the oxygen molecule or size of even H2O. H2O is water molecule. So once you achieve that, that water will not be that oxygen will not be going into the metal level to attack it. That's the philosophy being used here. These films are not continuous in nature. They are like you have a lubricating film. We have lubricating and lubricating. Some ions are getting attached to the metal and they are continuously going off and they are continuously generated. So you cannot make out whether the same this thing is there, but continuous film will be there onto the surface. Similarly, this kind of film, water film is generated, which is continuously going away and getting formed also at the same time. So greater attention must be given to pitting and crevice corrosion, which can be initiated under scale and biofouling layers into the water system. Means if at all you allow the scaling to take place, then lot of issues will take place into the condenser or into our system, and ultimately what we lose is energy. In many systems, corrosion products accelerate scale formation due to their seeding effect. This is called as corrosion fouling. And what happens is corrosion will make the metal surface congenial for deposition. Means if that surface is so smooth that the deposition cannot take place, or if it is that pitted, if it is there is a pitting corrosion or it is pitted, then tendency to form scaling can be higher, or deposition of algae can be higher. So basically it is called as corrosion fouling. Better understanding and theoretical modeling of both corrosion and scale formation is essential to see the water tendency for this process effectively. Means there are experts available in the market. So whatever you will be doing should be done with their consultation. Successful water treatment strategy must be thoroughly addressed to both corrosion and scale formation. The issues is not only corrosion and scale, the biological formation also, and the fouling issues also. So what are scale control technologies? Proper water treatment strategy should be there in consultation with the water experts. Use suitable anti-scalants like phosphates. There are so many phosphates, organic phosphates, phosphonates you can use. Acid dosing or pH control that needs to be taken care of. Mechanical or chemical cleaning, that is normally people combine both. And physical techniques like ultrasonic, magnetic fields, ion influx. So many technologies are available today in the market to take care of scaling or biological growth tendencies. So they need to be taken care of. Corrosion is fouling. Principal strategies are used for corrosion minimization or control in the water. Modify water quality by suitable water treatment process. See, whenever I used to go to the field when in my early years, or I used to tell people that we will convert water into DM water, and with DM water we will have this kind of chemistry so that the scaling tendency will be low and we can save on blowdowns. And that saving on blowdown, that energy cost was so high that it used to give payback on our investment. So modify water quality. Properly select suitable material of construction that we already spoke about, that neutrum. In case of seawater proximity or seawater use as a cooling water, cupronickel is used. Use of suitable corrosion inhibitors which are required. Film forming करनी है या what kind of corrosion inhibitors are required. Apply protective coatings, resistant linings, suitable paints, but these are external things. You cannot put it into water areas because they will be insulating in nature. And provide cathodic protection is, everybody knows that on the ship also there is a cathodic protection for the entire ship. So similarly, cathodic protection can be imparted. This is our third topic. Sir, are there any questions? I'm not able to see the again screen. Screen in the sense that bar here. Ah, yeah, got it. There is one question. Yeah, I standard we already spoke about. In our next session, we will be talking about water in HVAC. Means we will be talking about pre-commissioning wash, then water in condenser circuit, in evaporator circuit, impact of corrosion and scaling on the chiller performance, and water saving opportunities we have, those kind of opportunities. And somebody has suggested me to include some de-skilling aspects also. So I will be adding de-skilling here into our discussion. So next time is absolutely into our water, that is HVAC water. And these are all important areas of HVAC circuits we will be talking about. So with this, I say I say I say thank you. I say thank you very much for the people who are attending. I say thank you very much for Aarti and other HQ colleagues. And I say thank you very much. Raghavan sir, you are helping us so much. I owe you something. Thank you very much. I'm open to questions and answers. Next date is January 30th.
Yeah, next part 3 is on 30th January.
Yeah.
So thank you so much, Mr. Charu. It was very informative and interesting. We all really enjoyed. Let's just give 2 more minutes in case anyone wants to unmute and ask any question or share their inputs and suggestions
Yes.
to make the part 3 much more lively and more informative.
Yes, yes.
Aarti, will you be able to unmute the participants in case any of them want to ask any
Yes,
question?
sir. That is what I was typing. In case
Okay.
somebody is willing to say something, please raise your hand so I can unmute.
Or they themselves can get unmuted. Na?
I'm not sure, sir, if they would be able to do so.
Okay. Yeah.
I see few hands up. Siddharth, Sandeep Gupta, Srinivas.
So I shall unmute them one by one.
Okay.
Sir, can you hear me,
Sandeep
sir?
Gupta ji, namaste. Yeah, absolutely. You are absolutely audible.
Sir, regarding this CO2 in water, it becomes as, H2CO3 and it becomes acidic, no, sir? So whether we can allow that CO2 in
Yes,
water?
yes.
How to remove that
Yeah,
CO2?
you have no choice.
Ah,
There are ways to remove dissolved oxygen and dissolved CO2. Either you you put it into the system so that they can remove dissolved oxygen and dissolved CO2, or otherwise CO2, the way you said that it is acidic in nature, so you do it from that perspective, that take care of that pH.
pH we have to take.
Yeah, and then that will not allow the things to be there.
Yeah. Okay, sir. Thank you, sir.
Yeah. How to calculate? Mr. Nishan Gupta has asked this lead off. So Nishan ji, वो जो chloride है, chloride ions are generally not affected by any of these treatments. They are totally and completely unaffected. So they get concentrated. Okay, they get concentrated. So let's give you one example. In the initial water, it is 20 ppm. In the circulating cooling water, it is 400. That means 20 times it is concentrated. So when you divide 100 by 20, the blowdown is 5%. I'm giving you very simple phenomena here. Otherwise there is a pure engineering calculation which will give you 4.78 or something like that. But we are not bothered so much. We have to have that mota moti feeling. ये कितना आ रहा है? So 20 going up to 400, that means 20 times it is getting concentrated. 100 by 20 is 5. So 5% is the blowdown value. निशान जी, आप अनम्यूट करके पूछिए ना, बात कर सकते हैं.
Sir, one more question, sir. This cycle of concentration, COC, in cooling
That
towers.
is what COC is, what we talked about in cooling water. I was telling you how many times it is getting concentration. So 400 into cooling water and 20 into your makeup water. So 400 divided by 20 is 20 times COC. Means COC of your cooling water is 20. That means you are giving 5% blowdown.
So is it advisable to you continuous blowdown?
Actually, I do. If you really ask me, I follow no blowdown theory. I don't like to waste water, even a small drop of it. So, but philosophically, if you ask me, the lower the blowdown, the better it is. If at all you keep the higher blowdowns, that means you are wasting higher amount of water, throwing away higher amount of water, which should not be done by the normal professionals, I call it as. So
and even it increases the heat load because fresh water will be taken.
Yes, it drains off your energy. And if you are draining off chilled water like that, then it drains off your chilled water, means huge amount of energy is lost.
Yeah.
That is there. This is elaborated very greatly in our next session. That is on 30th.
Okay, sir. I'll join, sir. Thank you, sir.
Yeah. Then Ranjan Mahanta sir has asked me what is the TDS value for the chilled water system. Water is good. In case of chilled water, the TDS value has no value and meaning. See, these are the myths which are there into the industry, and I will tell you why I'm saying so. See, TDS is total dissolved solids. Total dissolved solids, to appear into the water or appear as scales, you require temperature. In case of chilled water, where is the temperature? There is no temperature. So in case of chilled water, you have to mitigate the problems which are associated with corrosion, which are associated with microbial contamination. And they appear as scale, not the TDS value appear as scale. So any amount of TDS value can go into chilled water. No problem on that. रंजन जी आप अनम्यूट करके पूछ सकते हो, बात कर सकते हो. Is there any other question?
Seems generally we have covered everything, Mr. Charu. So I want to
Yeah.
thank you very much and all the participants who very actively participated and gave some interesting questions also for discussion. So I thank all of you very much and also the HQ
Yeah.
team for providing all the required backend support. So we are all looking forward to the part
Yes,
3
sir.
concluding session, which is going to be much more relevant for what we do in HVAC. So that is happening on 30th, same time, 4 o'clock. So we are looking forward to again catching up with all of you. Thank you so much, Mr. Charu.
Yes.
Thank
Thank you
you.
very much. Again, I thank ISHRAE team, ISHRAE HQ, Aarti particularly, and Raghavan sir to you, and the participants who were there. The 30th one will be directly connected with our water. So the questions this time are of 30th also. Some questions are 30th. Those will be answered in 30th seminar. Thank you very much.